Hello everyone. So this is the second hour of electromagnetic induction. In this hour, we are going to talk about self-inductance, mutual inductance, and then we will talk about transformers. But in the entire lecture, there are very small things which are really important and a child should know. So beginning this hour with one such a small thing which is important and you must know. And this small thing is the relationship between flux and charge. Let's say we have got this loop, a conducting loop, and this is placed in a region where the magnetic field is changing. We know that a time varying magnetic field gives rise to electric field, and due to the electric field produced, there will be an EMF in the loop, and because of which the current will flow. Now when we say that the current will flow, what is current exactly? So the rate of flow of charge. So when some current flows in this coil, it means that some charge flows in this coil. Now the simple question is how much charge flows? So we can say that the EMF induced in the loop is nothing but minus d phi by dt, the rate of change of magnetic flux with respect to time. And we even know that the EMF induced in this loop will be the one responsible for driving some current in the loop. Let's say the current that moves in the loop is I and the resistance of loop is R. So you can say that the same EMF also has to be equals to IR. If we disregard this negative sign and just think about magnitude, so we can say that the rate of change of magnetic flux with respect to time equals to current times the resistance. And in place of current, we can always write the rate of flow of charge with respect to time. So we get another equation, that is d phi by dt, the rate of change of magnetic flux with respect to time, equals to the rate of flow of charge with respect to time multiplied by the resistance. Now we can cancel out dt both the side. Once we have cancelled out dt both the side, we get that d phi equals to dq into r. This means that the infinitely small change in flux equals to the infinitely small charge flow multiplied by resistance of the loop. Or we can rewrite it as dq equals to d phi by r. So we can write d phi equals to dq into r or dq equals to d phi by r. Now integrating both the sides, we can say that the total charge flow equals to the total change in the flux associated with this loop upon the resistance of the loop. So the total charge flow equals to the total change in flux associated with the loop upon resistance of this loop. And this is one important small correlation that you should know. What is the relationship between the change in flux and the charge flow in the loop? You will say that the charge flow in the loop is nothing but the change in the magnetic flux linked with the loop divided by resistance of the loop. Now let's see one beautiful question based on this. So the question goes like, there is a bar magnet and there is a coil. Now we are moving the bar magnet from some initial position to some final position. So the bar magnet goes from this initial position to this final position. One more time, the bar magnet is moved toward the coil from some initial position to some final position. Now question is, you are moving this bar magnet with two different speeds. In the case A, you are moving this bar magnet with a speed V, while in the case B, you are moving the same bar magnet but with double the speed, with a speed 2V. And then this question is asked. The question goes like, in which case the induced current is higher? In which case the induced current is higher in the loop? In the case A, the current is more, or in the case B, the current is more. And the second thing that is asked is here, in which case more charge flows through the coil? So the charge flow through the coil is higher in which case? In the case A, when you are moving the bar magnet with speed V, or in the case B, when you are moving the bar magnet with a speed 2V. So you will say that, sir, we know that the EMF induced in the loop equals to minus d phi by dt. Yes. So the higher the rate of change of flux, the more is the EMF. In the case B, you are moving the bar magnet with double the speed. When you are moving the bar magnet with double the speed, it means that the rate of change of flux is going to be double. From the same initial position, let's say for this position of bar magnet, the flux linked with this loop is phi 1. And for this final position, the flux linked with the loop is phi 2. If you move the bar magnet quicker, the same change in flux will take place, but in lesser amount of time. So as the EMF induced is the rate of change of flux with respect to time, in the case B, when the bar magnet moves faster, the flux will change at a higher rate. And when the flux will change at a higher rate, the EMF induced in the loop will be higher, and so will be the induced current. So we say that as the rate of change of flux is higher in case B, as the rate of change of flux is higher in case B. Why? Because the bar magnet moves faster. so is the induced EMF. And when the induced EMF will be higher, so is the induced current. Because we know that induced EMF equals to the induced current in the loop times the resistance of the loop. So since in the case B, the bar magnet moves at double the speed, the rate of change of flux will be double. Hence, the EMF induced will be double and the rate of flow of charge, which is current, will be double. Now let's answer the second part of question, which is in which case more charge flows through the coil. So we have just learned that the charge that flows in the coil is nothing but the change in flux upon resistance. For the same initial and same final position of bar magnet, the change in flux in both the cases is same irrespective you are moving the bar magnet quicker or slower. Since the change in flux is same, the charge flow will be same. So here you can say that at the change in flux is same in both the cases, so the same amount of charge flow. Or you can think of it this way as well. What is current? Sir, the rate of flow of charge with respect to time, yes. So can you say that the total charge flow equals to current into time? In the case B, the speed is double. So the EMF is double. So the current is double. So current is double. But since the bar magnet moves at double the speed, the time taken to reach the final position will be half. So if the current becomes double but the time for which that current flows become half, what will you say about the total charge flow? So sir, current is becoming double but the time becomes half, that's why the total charge flow has to remain the same. Yes. Now let's move on and understand about inductance. What exactly is inductance? And here the definition plays the most crucial role. So understand the definition of inductance and this hour will be super simple. So what exactly is inductance? The property of a substance by the virtue of which it opposes the change in current. Change in current. Inductance is the property of the substance by the virtue of which it opposes the change in current. And inductor has got no problem about how much current is flowing through it. It has got problem with the change in current. We know that there is another property of substance called resistance. What exactly is resistance? The property of a substance by the virtue of which it opposes the flow of current. So resistance has got a problem with the flow of current, right? But the inductance has got a problem with the change in current. Now what I have drawn just now, which looks like a solenoid, is the symbol for inductor, and the unit of inductor in the SI system is Henry, or sometimes denoted as capital H. Now let's say you have an inductor and a huge current of 10,000 ampere flows through it. Inductor has got no problem with how much current is flowing through it. Inductor has a problem with that this current shouldn't change. If the current of 10,000 ampere is flowing and it is constant, inductor has got no problem with it. But if this current tries to change, it has got a problem with it. It tries to oppose the change in current. But why will anything try to oppose the change in current? Let's understand it. Let's say we have got a coil, yes, and in this coil a current I is flowing. We know that when a current I flows in a circular coil of, let's say, having n turns, then the magnetic field at the center of coil is given by the number of turns multiplied by the magnetic field produced at the center by one turn. And the magnetic field produced at the center by one turn will be nothing but mu naught I by 2r, where r is the radius of this coil. You can see that if the current in the loop changes, if the current in the coil changes, so does the magnetic field at the center. If the magnetic field at the center of the coil will change, it will change at other places as well. So the flux linked with the coil will change. And whenever the flux linked with the coil will change, an EMF will be induced which tries to oppose the change in flux. But you need to ask yourself, why is the flux changing at the very first place? Sir, as the current is changing, so is the magnetic field. As the magnetic field linked with the loop changes, so does the flux. And every time the flux changes, an EMF is induced which try to oppose the change in flux. So as to oppose the change in flux, it tries to oppose the change in magnetic field. And so as to oppose the change in magnetic field, it tries to oppose the change in current. So sir, what are you trying to explain here? I'm trying to explain from where does this property of inductance comes. The property of inductance is the property of a substance by the virtue of which it opposes the change in current. But why will anything oppose the change in current? For the simple reason, Current produces magnetic field produces magnetic flux. When the current changes, the field changes, the field changes, the flux changes, and when flux changes, an EMF is produced which tries to oppose the change in flux. And the flux is changing because the field is changing. So the EMF produced tries to oppose the change in magnetic field. And the field is changing because current is changing. So the EMF produced tries to oppose the change in current. Okay, so once more, as the current changes, so does the magnetic field linked with the loop. As the magnetic field changes, so does the flux linked with the loop. So when current changes, magnetic field linked with the loop changes and the flux linked with the loop changes. So an EMF is induced which tries to oppose the change in flux. So oppose the change in magnetic field, because so as to oppose the change in flux, you have to make sure that the magnetic field strength do not change. And for the magnetic field strength to remain the same, the current shouldn't change, and hence change in current. Now we know that the flux linked with the loop is directly proportional to the magnetic field at the points within the loop, and that is directly proportional to the current flowing in the loop. So as the EMF equals to minus d phi magnetic by dt, we can also write this EMF to be proportional to the rate of change of current with respect to time. Why? Because the flux is directly proportional to magnetic field and magnetic field is directly proportional to current. So EMF, which is equal to minus d phi by dt, is also directly proportional to di by dt. So this is the equation we get. Now every time in this world a physicist find a proportionality, what do? They place a proportionality constant. So we write E equals to minus L di by dt. Here the proportionality constant is L. L stands for inductance. Now bachcho, here important thing. Why do we have a minus sign? For the same reason we have a minus sign in E equals to minus d phi by dt. The EMF induced will be such that it will oppose the change in flux. Similarly here you will say that the EMF induced will be such that it will oppose the change in current. So E equals to minus L di by dt. So now we will learn an important correlation to determine inductance of different bodies. So the relationship between current flowing, the flux linked, and the inductance. We have just learned that the EMF induced in the coil equals to minus times the inductance of the coil times the rate of change of current with respect to time. And from Faraday's law, we already know that the EMF induced in the coil is nothing but minus times the rate of change of magnetic flux linked with it with respect to time. So we can cancel out this minus and dt and dt. And once we have cancelled them out, we can see that d phi equals to LDI. What is the meaning of d phi equals to LDI? The infinitely small flux linked with the coil equals to inductance of the coil times the infinitely small current flowing through it. Now if we integrate this thing both the side, we can say that the flux linked with the coil equals to the inductance of the coil times the current flowing through it. Once more, the flux linked with the coil equals to inductance of the coil times current flowing through it. These are small correlations which many a time students don't know, and hence they don't know how to solve a bigger question. This is one small thing that you must know. The flux linked with the coil equals to the inductance of the coil times the current flowing through it. Now we will use this to determine the self-inductance of a solenoid. How to determine the inductance of a solenoid? We will assume that some current I flows through it. And when some current I flows through the solenoid, we will find out what is the flux linked with it. And we will say that the flux linked with the solenoid equals to something times the current flowing through it. And this something has to be the inductance of the solenoid. So let's see. Let's say we have got this solenoid, and this solenoid has a length L, a current I flows through it, and the cross-sectional area of this solenoid is A. Let's say the number of turns on this solenoid is N, and the number of turns per unit length is a small n. So you know that the number of turns per unit length is nothing but the overall number of turns divided by length. You will say that the magnetic field inside the solenoid will be nothing but mu naught Ni, where mu naught is the permeability of free space, N is the number of turns per unit length, and I is the current flowing through the solenoid. What is our mission? The mission is to find inductance of the solenoid. Sir, how do you wish to do it? I will assume that some current I flows through it, and then I will find the flux linked with the solenoid due to this current, and the flux link equals to something times I, and that something is the inductance. So when a current I flows through the solenoid, a magnetic field mu naught and I is created inside it. Now you can say that the flux linked with one turn of the solenoid has to be equals to the magnetic field strength times the cross-sectional area of one turn. So you will say that the flux linked with one loop will be equals to BA. And in place of B, you can substitute mu naught and I. So the flux linked with one loop will be mu naught and I into A. This will be the flux linked with one loop on the solenoid. Our mission is to determine the inductance of the entire solenoid, right? So we will say that the flux linked through one loop is mu naught NIA. So the flux linked through all the loops will be nothing but the number of turns times the flux linked with one loop. Now, if the number of turns are capital N, and we know that the flux linked with one loop is mu naught NIA, substituting it, we will say that the flux linked with the entire solenoid equals to N times mu naught NIA. Now, comparing this with flux equals to Li, we can say that if you take I outside, everything else is your inductance. So the self-inductance is nothing but mu naught NNA. Now beta, in place of this number of turns, you can write number of turns per unit length multiplied by length. So you will get L equals to mu naught N into NL into A, that becomes mu naught into N square LA. Or here in place of the number of turns per unit length, small n, you can write number of turns upon length. So you will get mu naught into N by L into N into A. So you can even write the same inductance as mu naught N square by LA. So do you remember this formula? I will say I don't. Then sir, how do you write it when it is required in a paper? It takes me exactly 10 seconds to do it. The magnetic field is mu naught Ni. So I keep on writing like this. The magnetic field is mu naught Ni. So the flux linked with one turn is mu naught Nia. So flux linked with entire loop is N mu naught Nia. And this part apart from I is my inductance. So how do I write it? Okay. So I think of it quickly as, okay, the magnetic field is mu naught Ni. If the magnetic field is mu naught Ni, so the flux linked with one turn is mu naught Nia, and the total flux linked is N times of this, and apart from I, whatever I have here is my self-inductance. So keep this thing in mind, and now first of all let's study the energy stored inside an inductor before we understand more on this. Now what is the energy stored inside an inductor? Remember that when I taught you capacitor, I said that between the plates of capacitor, energy is stored in the form of electric field. And the energy stored per unit volume in the form of electric field is given by half epsilon naught E square, right? Similarly, you need to remember that inside an inductor, energy is stored in the form of magnetic field. Every time they say an inductor, think of a solenoid beta. So energy is stored inside an inductor in the form of magnetic field. And just like for electric field, the energy stored per unit volume is given by half epsilon naught E square. For magnetic field, the energy stored per unit volume in the form of magnetic field is defined how? So remember that beta. Half epsilon naught E square for electric field. So if for magnetic field half is half, you can't change that. Okay. Remember that in the entire course of electricity, you always find epsilon naught in the denominator, and in the entire course of magnetism, you find mu naught in the numerator. Here for electric field, you get the energy stored per unit volume as half epsilon naught E square. So you do not get mu naught in the numerator, you get mu naught in the denominator here. So this is the only time you find usually mu naught in the denominator. And in place of electric field, you simply write magnetic field whole square. So remember that energy stored per unit volume in the form of electric field is half epsilon naught E square. Energy stored per unit volume in the form of magnetic field is given by B square by 2 mu naught. Now you can even say that from here the energy stored inside the inductor is nothing but B square upon 2 mu naught multiplied by the volume of the inductor. Whenever they say an inductor, think of a solenoid. So let's say we have got here a solenoid having a cross-sectional area A, having a length L, number of turns per unit length is small n, and the number of turns N. Your mission is to determine how much energy is stored within this solenoid in the form of magnetic field. So you will say that the magnetic field strength inside the solenoid is given by mu naught Ni. Yes sir. And we know that the energy stored inside this solenoid has to be equals to B square by 2 mu naught into the volume of solenoid. In place of magnetic field, you can substitute mu naught Ni. In place of volume of this solenoid, you can substitute the cross-sectional area times length. So you get that energy stored inside the solenoid equals to the magnetic field strength inside it whole square, mu naught Ni whole square, upon 2 times of mu naught from the formula multiplied by the volume in which this magnetic field is present, which is cross-sectional area times length Al. Now bachcho, from here you can write this mu naught Ni whole square as mu naught square N square I square. So you will get the energy stored as half mu naught N square Al I square. Open it up and solve it. You will get mu naught square N square I square upon 2 mu naught times Al. So beta 1 mu naught will get cancelled with 1 mu naught. So you will get half into mu naught into N square into Al into I square. We have just done that. The self-inductance of the solenoid is given by mu naught N square Al. This is one of the formulation we have just learned. So in place of this mu naught N square Al, you can write the self-inductance. So remember that the energy stored in the form of magnetic field inside the inductor is given by half Li square. And this is the beauty of physics. The energy formula always comes out to be half something something square, half mv square, half kx square, half cv square, half Li square. So easy to remember. So what are the key points you need to remember here? First thing, energy is stored inside the inductor in the form of magnetic field. The energy stored inside an inductor when a current I flows through it is given by half Li square. So let's move on and talk a little bit about coil. What is a coil? Sir, a coil. A coil. You take a wire, you turn it around, that becomes a coil. Okay. Now what I'm trying to tell you here about coil will be useful both in this chapter as well as in the chapter of alternating current, which is our next hour. So when a current flows through the coil, we know that it is made up of wire, it is made up of metal, so it must have some resistance. Also, when the current flowing through the coil changes, it changes the flux linked with it, so it has got some inductance. So whenever they tell you think of a coil, always think of a resistor and an inductor in series. So every time you have to think of a coil, think of a resistor and an inductor in series every time. So now on inserting an iron rod inside an inductor, or think of a solenoid, we know that iron is ferromagnetic in nature. For ferromagnetic materials, the relative permeability is greater than 1, is of the order of thousands. So when you place an iron rod inside an inductor, what happens is, if you drive some current I, now the magnetic field within the core of solenoid becomes 1000 times larger, manifold. So as the magnetic field strength becomes very high, the flux link becomes very high for the same current flow. And we know that the flux link equals to self-inductance times current. So for the same current, after inserting the ferromagnetic material inside the solenoid, the flux linked with the solenoid becomes very large. It means that the self-inductance becomes very large. So if you have got this solenoid and you have inserted an iron rod in it, which is a ferromagnetic material, we know that as the magnetic field and flux becomes manifold, many times larger for the same current, we say that the inductance becomes manifold. So remember that when you insert an iron rod inside a solenoid, its inductance becomes very large. So now we will talk about inductors connected to an ideal battery. So let's say you have a pure inductor which has got no resistance and an ideal battery which has got no resistance. And let's say you turn the key on. We know that on turning the key on, some current will flow in the circuit. Our mission is to determine the current at any time t. So how to write the equation of KVL for this particular loop? Now understand that physicists are not dumb people. When they say that the EMF in the inductor equals to minus L di by dt, they place here a minus sign for a reason. Now understand this, how to write the potential drop across an inductor. Let's say I take the potential of this point as x. So the potential of this point, you are jumping across an ideal battery, right? So the potential of this point will be x plus e. The potential of this point will be x plus e. So when you write the equation x from the first point plus e to the second point, same at the third point. Now when you are moving in the direction of current across an inductor, the potential drops by minus L di by dt. So you will write x plus E minus L di by dt equals to x. Now cancelling out x both the side, you can write E minus L di by dt equals to 0. So E minus L di by dt equals to 0, or you can write E equals to L di by dt. Now any child might say, sir, you are such a time waster. You could have just worked on the magnitude. You could have said that the potential drop across the ideal cell E has to be same as the potential drop across the inductor, which is L di by dt, and you would have directly got this equation. What I have just told you, how to write the potential drop across an inductor, is important for solving circuit question, and I will explain it again. Just stay tuned. Now you can bring this dt to the left hand side and write integral L di equals to integral E dt. Now L and E are constant. You can take them out of the integration and write Li equals to Et, or the current flowing at any time t equals to E by L into t. So once we know that the current flowing at any time t equals to E by L into t, we know that for such a circuit, the current is directly proportional to time. And if you visualize the current time graph, you will get a straight line passing through the origin. Now do understand, in this circuit we had no resistance at all. So the current will keep on growing linearly. Once more repeating the important line, inductor has got no problem with the flow of current. Inductor has got problem with the change in current. So let's move on and understand EMF across an inductor. Let's say we have got this inductor. In the inductor, current is flowing from left to right. Current is flowing from left to right. Question is, the EMF induced in this inductor will be like this or like this, like option 1 or option 2. Which side of the inductor will have higher polarity? So you will say that, sir, see, current is from left to right and the current is increasing. The property of inductance is to oppose the change in current. Current is from left to right and current is increasing. The inductive nature will try to stop this current from increasing. So if it has to stop this current from increasing, the potential created by the induced EMF will be higher towards the left hand side. It will try to block the flow of this current. It will try to drive current in the opposite direction. Let's see one more example. Let's say current is from left to right but decreasing. Inductor has got problem with the change in current. If the current increases, it will be such that it will try to decrease it. If the current decreases, the EMF will be such that it will try to increase it. So now, since the current is from left to right and decreasing, the inductor will try to increase the current towards right. And so as to increase the current towards right, the polarity has to be higher towards right. Let's see the next example. Let's say the current is from right to left and increasing. So current is from right to left and increasing. It will try to oppose the change in current. So it will produce an EMF to oppose the change in current. Current is from right to left and increasing. So as to keep it under control, so as to oppose the change, this inductor will produce an EMF keeping the right hand side at higher polarity. Let's think of one more case. The current is from right to left and decreasing. The current is from right to left and decreasing. So it will produce an EMF so as to oppose the change in current. Current is from right to left and decreasing. So it will try to increase it towards left. So the polarity will be higher towards left. And believe me, you won't need to use these while solving circuit, because I will teach you the most appropriate method to write the equation here. So let's say you have got this circuit. Here you can see a battery of 6 volt, an inductor of 2 Henry, a resistance of 1 ohm, and a current of 2 ampere is flowing in the circuit right now. Your mission is to determine what is the rate of change of current in the circuit right now. What is the value of di by dt? Sir, how to do it? It's quite easy. If you take the potential at this point as x, the potential at this point will be x plus 6. The potential at this point will be again x plus 6. Now, when you move across the inductor, the potential drop arises due to the change in current. Remember that when you move in the sense of current, the potential drops by minus L di by dt. So you will write minus L2 into di by dt. So now you have reached this point, you have jumped across the inductor. Now when you jump across the resistor, the potential drop comes as per the Ohm's law. So the potential drop has to be IR. Current in the loop is 2 and the resistance is 1. So going from left to right in this resistor, the potential will drop by minus of I into R. And once you have reached this point has the same potential as X. So cancelling out X and X, you will get 6 minus 2, which is 4, equals to 2 di by dt. Or you will say that di by dt equals to 2 ampere per second. Okay. So starting from here, you will write X plus 6, X plus 6. Jumping from here to here, you will write X plus 6 minus 2 di by dt. Jumping from here to here, you will write minus IR because you are moving in the sense of current. Current is 2, resistance is 1, so minus IR minus 2. And this has to be equals to X. Now, bachcho log, cancelling out X and X. And from this 6 minus 2, you will get 4. So you can write 2 di by dt equals to 4. Hence, bachcho, di by dt comes out to be 2 ampere per second. Do understand that when you get di by dt as positive number, it means that the current is increasing. If you get di by dt as a negative number, it means that the current is decreasing. So here di by dt came out to be plus 2 ampere per second. It means that the current increases at the rate of 2 ampere per second. So the current is increasing as the sign of di by dt is positive. Let's see one more example to understand it. Find the rate of change of current in the circuit at this instant. So here you have got this circuit. In the circuit you have a battery of 12 volt, a current of 2 ampere, an inductor of 1 Henry and a resistance of 4 ohm. Your mission is to find the rate of change of current in the circuit at this instant. So sir, what to do? Start going once around the loop and write the equation. So here, visualize that this point has got potential of X. Going from here to here, there will be no potential change, again X. When you move in the sense of current across the inductor, you write the potential drop as minus L di by dt. So if the potential of this point is X, this point is also X, the potential of this point will be X minus L1 into di by dt. Now jumping from here to the right of the resistor, you know that when you move in the direction of current, the potential drops across the resistor. So going from left of the resistor to the right of resistor, the potential will drop by I into R, 2 into 4, so minus 8. And then all these points will be at same potential. Then plus 12 gives you X. Now solving this, you can find out the value of di by dt. So we can write X minus L into di by dt, inductance is 1, minus 8 I into R, 8 jumping from here to here. And then going from here to here, you do a plus 12 equals to X. Now but you cancel out X and X, you will write that 1 into di by dt comes out to be equals to 4. Again, the positive sign tells you that the current is increasing. If you get di by dt equals to negative, it means that the current in the loop is decreasing. So you will say that the positive sign tells us that this current increases with time. Now, but here one important thing where I want to emphasize. We say that the potential drop across the inductor equals to minus L di by dt. You have to move in the sense of current. So if the current is from left to right, on going from left to right, you will decrease the potential by an amount L di by dt. If you are moving in direction opposite to current, you will do a plus. So I will simply say, just go in the sense you have assumed the current to be in the loop. When you move in the sense of current, you have assumed, simply write the potential drop to be minus L di by dt. That is the basic definition. Okay. So now we will talk about initial and steady state. Now these are the states from where questions are asked in examination. That just after turning the key on, what is the current in the inductor? And what is the current flowing through the inductor after a long time? As a matter of fact, before continuing to teach you this, I will like to tell you in NEET 2020, not even a single question came from circuit-based problems. But circuit-based problems are my personal favorite and they used to come every year, leave out the NEET 2020. So I say on the probability matrix, this year there is a higher probability of circuit-based question coming. So this topic becomes important, the initial state and steady state. Now, do understand that there can't be any finite change in the current flowing through the inductor in an infinitely small frame of time. Why? We know that the EMF across the inductor is given by minus L di by dt. If somebody says that for the current flowing through the inductor, there is a finite change in current in an infinitely small frame of time, then the EMF will be equals to minus L into that finite change in current upon infinitely small frame of time. The denominator is infinitely small while the numerator is finite, so you will get an infinitely large EMF. Do understand that an infinitely large EMF will be required to change the current by a finite amount in an infinitely small frame of time, since you can't provide infinite EMF. Hence, there can't be a finite change in the current flowing through the inductor in an infinitely small frame of time. Once more repeating, if you have an inductor, there can't be any finite change in the current flowing through it in an infinitely small frame of time. Because if there will be a finite change in current in an infinitely small frame of time, the numerator is finite, but the denominator is infinitely small. Think of the denominator to be 0.00000000000000000 and then a 1. So the EMF comes out to be something finite upon an infinitely small number that comes out to be infinitely large. So do understand that an infinitely large EMF will be required to produce a finite change in current in an infinitely small frame of time, and you are not going to get infinite EMF. So the counter argument comes like, in an infinitely small frame of time, the change in current flowing through the inductor can only be infinitely small. In an infinitely small frame of time, the change in current flowing through the inductor can only be infinitely small. Hence, remember this statement. The current flowing through an inductor can't change suddenly. Why? Because in an infinitely small frame of time, the change in current can only be infinitely small. So you can't have the current flowing through the inductor change suddenly, because if the current changes suddenly, you have got a finite change in an infinitely small frame of time, and for that you will require infinite EMF. So remember the first statement, the current flowing through an inductor can't change suddenly. The current flowing through an inductor can't change suddenly. The second point, at steady state, also called at time equals to infinity. At steady state, what is the meaning of steady state? Sir, steady, not varying anymore. So once the circuit attains a steady state, the current in the circuit becomes constant. If the current flowing in a particular line of the circuit becomes constant, if the current is constant, you will say that di by dt has to be equals to 0. The rate of change of current with respect to time is 0. And we know that the EMF induced across the inductor equals to minus L di by dt. At steady state, at time equals to infinity, the current becomes constant, the di by dt is 0, the di by dt is 0, so I can say that the EMF across the inductor is 0. And if there is no potential drop across the inductor, it is as good as it is a wire. So just remember that at steady state or at time equals to infinity, the current flowing through the circuit becomes constant. So as the current becomes constant, di by dt becomes 0. So you will say that the EMF equals to, which is equal to minus L di by dt, becomes equals to 0. And once you know that the EMF becomes 0, you can simply replace the inductor with a wire. Why? Because sir, it's a steady state. Now things are constant. Current is constant. Di by dt is 0. Di by dt is 0. Potential drop across the inductor is 0. Potential drop across the inductor is 0. So there is no potential drop across it. It acts just like a wire. So here, to find the current in the circuit at the initial state or at the steady state, you need to remember these two statements. The first statement, the current flowing through an inductor can't change suddenly. And the second statement, at steady state, just replace the inductor with a wire. Why should you replace the inductor with a wire, sir? Current became constant, di by dt is 0, di by dt is 0, the potential drop across the inductor is 0. As the potential drop across the inductor is 0, you can just replace the inductor with a wire. Okay. Now, let's say you have got this circuit. In this circuit, you can see that there is a battery of 12 volt, there is an inductor of 2 Henry, and there is a resistance of 3 ohm. Now, once you turn the key on at time equals to 0, question is just after turning the key on, what is the current in the circuit? So you will say that, so the first statement, the current flowing through the inductor can't change suddenly. Just before turning this key on, the key was open, so there was no current in the circuit. So even just after turning the key on, the current flowing through the inductor can't change suddenly. So it will remain equals to 0. So you will say that just after turning the key on, the current in the circuit is 0, because just before turning the key on, the current in the circuit was 0, and the current in the inductor can't change suddenly. To have a sudden change in the current flowing through the inductor, the amount of EMF required will be infinite. So at time equals to 0, just after turning the key on, the current in the circuit is 0. The second part, what is the rate of change of current in the circuit? So you will say, sir, just after turning the key on, at time equals to 0, the current in the circuit is 0. So the potential drop across the resistor has to be 0. Potential drop across the resistor has to be equals to I into R just after turning the key on at time equals to 0. Since the current is 0, so the potential drop across the resistor is 0. This means that the potential drop of 12 volt takes place across the inductor. So you will say that the EMF across the inductor equals to LdI by dt. So the potential drop of 12 volt across the inductor equals to its inductance 2 multiplied by di by dt. So you will write at time equals to 0, just after turning the key on, di by dt will be equals to 6 ampere per second. So now let's talk about time equals to infinity. At steady state, what will happen? Beta, just remember, for steady state, replace the inductor with a wire. At steady state, di by dt has to be 0. We already know. What will be the current in the circuit? Replace the inductor with a wire and you will have a circuit with a battery of 12 volt and a resistance of 3 ohm. So the current in the circuit at time equals to infinity will be 4 ampere. And the rate of change of current in this circuit will be 0. So let's practice out more questions based on this. Here we have a question where we have an inductor of 4 Henry, a resistance of 2 ohm and a battery of 6 ohm. Question is, determine the current and the rate of change of current in the circuit at time equals to 0 and determine the current and rate of change of current at time equals to infinity. You will say that, so just after turning the key on, that is at time equals to 0. Just before turning the key on, the circuit was open. So no current was flowing. We know that the current in the inductor can't change suddenly. So just after turning the key on, the current flowing through the inductor has to be 0. So I already know the answer to this is 0. Next part, I know that at steady state current becomes constant. Since the current becomes constant, di by dt has to be equals to 0. So I know also answer of this part has to be 0. Now how easy it is. Just after turning the key on, that is at time equals to 0. You know that the current in the circuit is 0, so no potential drop across the resistor. Potential drop across resistor equals to I into R. Since there is no potential drop across the resistor, it means that the entire potential drop of 6 volt takes place in the inductor. So you can write 6, the potential drop across the inductor equals to L di by dt equals to 4 into di by dt. So bachcho, from here you get di by dt equals to 6 by 4, which is 3 by 2, which is 1.5 ampere per second. This is your di by dt. Okay. Now, next part. What is the current at time equals to infinity? So we have learned that at time equals to infinity, at steady state, since the current becomes constant, di by dt is 0, potential drop across the inductor is 0. Since the potential drop across inductor is 0, it's better to convert it with a wire. And when you replace it with a wire and close the circuit, you will say that the battery is of 6 volt, resistance is 2 ohm, so the current has to be 6 by 2, 3 ampere. This is how easy the questions are. So just after turning the key on, you will say that current in the circuit will be 0 because just before it was 0 and the current flowing through the inductor can't change suddenly. What will be the value of di by dt? You will say that the entire potential drop of now 6 volt just after turning the key on will take place across the inductor because there is no current, so no potential drop across the resistance. So 6 equals to 4 di by dt, so di by dt comes out to be 1.5 ampere per second. Again, the positive sign tells us that the current is increasing. For second part, at time equals to infinity, we know that we have attained steady state. So at time equals to infinity, di by dt will be equals to 0. And we will just replace this inductor with a wire and think of the closed circuit. And we will say that the current in the circuit has to be equals to EMF divided by resistance. So that will be equals to 6 by 2. That will be 3 ampere. Okay. Now let's talk ahead. So before we move on to understand mutual inductance, let's learn series and parallel combination of inductors. Now this is way easy. Just remember one line: inductors like resistors. Inductors like resistors. So if you have got series combination of inductors and there are multiple inductors having inductance L1, L2 and L3, and you wish to replace all these three and place a single inductor, then what has to be the equivalent inductance for that single inductor? So you will say that the equivalent inductance for this single inductor has to be nothing but the sum of the individual inductances. So L equivalent equals to L1 plus L2 plus L3, just like resistors in series. And if you have got parallel combination, then if you have got multiple inductors, each of inductance L1, L2 and L3 in parallel, and you wish to replace all of them and place a single inductor, then I said already, it's just like resistors. So you will say that 1 by L equivalent equals to 1 by L1 plus 1 by L2 plus 1 by L3 and so on. So the things which we have here learned for resistors, like if you place n identical resistors in series, the equivalent resistance becomes NR. If you place n identical resistors in parallel, the equivalent resistance becomes R by N. Those things can be applied here as well. So now without wasting time, let's start talking about the second important thing of this hour, which is mutual inductance. So mutual inductance, what is the meaning of it? Let's say you have got two coils placed nearby. In self-inductance, when the current flows through the first coil, it produces a magnetic field at its old coil position. Hence, the flux is linked with its own loop, and when the current changes, the flux changes. But here we are talking about two coils. Let's say when we drive some current in the first coil, it produces some magnetic field. Now, these magnetic field lines crosses even the second coil. When the current in the first coil changes, the magnetic field at the position of second coil changes. Due to the change in the magnetic field strength at the position of second coil, you will say that the flux linked with the second coil changes, and when the flux linked with the second coil changes, an EMF is induced in the second coil which tries to oppose the change in this flux. So you will say that since if a current flows in the first coil, it produces some strength of magnetic field at the position of second coil. When the current in the first coil changes, the magnetic field at the position of second coil changes. As the magnetic field at the position of second coil changes, the flux linked with the second coil changes. When the flux linked with the second coil changes, an EMF is induced in the second coil due to the change in current in the first coil. So we say that an EMF is induced in the second coil due to the change in current in the first coil, and this EMF is directly proportional to the rate of change of current in the first coil with respect to time. Similarly, if some current flows in the second coil, there will be some magnetic field at the position of first coil due to the current in the second coil. When the current in the second coil will change, the strength of magnetic field at all these points will change. Hence, the flux linked with the first coil will change. Hence, an EMF will be produced in the first coil due to the change in the current in second coil. So, similarly, you can write E1 is directly proportional to di2 by dt. So, due to the change in current in first coil, an EMF is generated in second coil, and the EMF generated in second coil is directly proportional to the rate of change of current in the first coil with respect to time. Similarly, when the current changes in the second coil, an EMF is produced in the first coil, and the EMF produced in the first coil is directly proportional to the rate of change of current in the second coil. Now, every time a physicist finds a proportionality, what do? So they place up a proportionality constant. So here we place a proportionality constant, and we say that the EMF linked with the second coil equals to minus times the mutual inductance at the position of second coil due to the first coil into di1 by dt. And we say that the EMF induced in the first coil due to the change in current in the second coil is given by E1 equals to minus times mutual inductance of the first coil due to the second coil times di2 by dt. Now you do not need to remember this 2, 1 and 1, 2. Why? Because there is a beautiful principle involved, that is called the principle of reciprocity. The principle of reciprocity tells us that the mutual inductance of second coil due to the first coil is same as the mutual inductance of first coil due to the second coil, and if they are same, why to give them two different names? So we just place a single symbol which is called M. So from the principle of reciprocity, we know that the mutual inductance of second coil due to the first coil is same as the mutual inductance of first coil due to the second coil. Hence, they are same thing. So we give them a single name and call them M. So remember that the EMF induced in the second coil equals to minus mutual inductance times the rate of change of current in the first coil with respect to time. and the EMF induced in the first coil equals to minus of the mutual inductance times the rate of change of current in the second coil with respect to time. So remember that E equals to minus M di by dt. Again, the minus sign represents the same thing, that the EMF induced is such that it will try to oppose the change in current. So now let's understand one more relationship between the flux, mutual inductance and current, so that we can determine the mutual inductance of systems. So what is the relationship between mutual inductance, current and the flux? We have just learned that if you have got two coils, then the EMF induced in the second coil due to the change in current in the first coil is given by minus M di1 by dt. And you even know that the EMF induced in the second coil can also be written as minus times the rate of change of magnetic flux with the second coil. So you can even write the same EMF induced in the second coil to be equals to minus d phi 2 by dt. Now if you know that minus M di1 by dt equals to minus d phi 2 by dt, beta first of all cancel out this dt minus minus. So what you say, that the infinitely small change in the flux in the second coil equals to mutual inductance times the infinitely small change in the current in the first coil. So you will say that on cancelling out, phi 2 equals to Mi1. The flux linked with the second coil equals to mutual inductance times the current flowing in the first coil. Once more, the flux linked with the second coil equals to mutual inductance times the current flowing in the first coil. Just like to determine the self-inductance of a solenoid, I said that the flux linked with the solenoid equals to its self-inductance times the current flowing through it. Here we are talking about mutual inductance of one due to the other. So we say that the flux linked with second coil equals to mutual inductance times the current flowing in the first coil. So now we are going to use this relationship to determine the mutual inductance of the system. So I will tell you to focus here once more. Every time I will assume that in the first coil there is some current. Then I will find out what is the flux linked with the second coil due to this current. Then I will write the flux linked with second coil equals to something times the current flowing in the first one. And then I will say this something is the mutual inductance. How? Let's practice. So the first case, mutual inductance for big and small coil. Let's say you have got two coplanar coils. A very big coil of radius A and a small coil of radius B. The bigger coil has got N1 number of turns and the smaller coil has got N2 number of turns. Your mission is to determine the mutual inductance of this pair of coil, given that the radius of the smaller coil is very small compared to the radius of the bigger coil. So B is very small compared to A. Since B is very small compared to A, you can assume the smaller coil to be placed at the center of the bigger coil. What is our mission? Our mission is to determine the mutual inductance. Sir, how to do? We say that the flux linked with 2 equals to mutual inductance times the current flowing in 1. So assume that in the bigger coil, some current I1 is flowing. And find out the flux linked with this smaller coil due to the current in the bigger coil. And that flux linked with the smaller coil equals to something times the current in the bigger coil, and this something is your mutual inductance. So how to find? Let's see. Assume that some current I1 flows in the bigger coil. So you will say that the magnetic field by the bigger coil at the position of smaller coil will be equal to the number of turns in the bigger coil multiplied by the field produced by one of its turns, which is mu naught I1 by 2A. Now this is the strength of magnetic field produced by a current I1 flowing in the bigger coil at the position of smaller coil. What will be the flux linked with the smaller coil? You will say that the flux linked with the smaller coil will be equals to the number of turns multiplied by flux linked with one turn. And you can write this flux linked with one turn as the magnetic field strength, which is N1 into mu naught I1 by 2A multiplied by the area of this smaller coil, which is pi p square. That's how easy it is. So you will say phi 2, the flux linked with the smaller coil, equals to number of turns in the smaller coil multiplied by the strength of magnetic field at the position of smaller coil multiplied by its area. Now you can say phi 2 equals to something times I1. And this something is your mutual inductance. So you will say that phi 2 equals to mu naught N1 N2 into pi b square upon 2A into I1. So this whole part has to be your mutual inductance. Hence the mutual inductance will be mu naught N1 N2 pi b square upon 2A. Sir, do you remember this result? No. Then how do you do it in paper? Beta, I follow the process. I remember that the flux linked with 2 equals to mutual inductance times the current flowing through 1. I remember this thing, yes. And once I remember phi 2 equals to mi1, it takes me only 10 seconds to reach this result. I keep on writing. Do understand that if the smaller coil is placed in such a way that its plane is perpendicular to the plane of the bigger coil. If the smaller coil is placed such that its plane is perpendicular to the plane of bigger coil, then the bigger coil will produce a magnetic field at the position of smaller coil. But the area vector of the smaller coil will be perpendicular to this magnetic field. Hence the flux linked will be 0 because the magnetic field line won't cross it. As the flux linked will be 0, you will say that the flux linked with the smaller coil due to the current flowing in the bigger coil is 0. Hence the mutual inductance has to be 0. So if the plane of the small coil is perpendicular to the big coil, then the flux link is 0 and hence the mutual inductance is 0. So orientation also matters. So let's practice more question and find out the mutual inductance every time. So let's think of the second case. Here you have got two coaxial coils. They have got the same axis. The bigger coil has a radius A, the smaller coil has a radius B. The bigger coil has N1 turn, the smaller coil has N2 turn, and the separation between their center is X. The smaller coil is very small, okay, of radius B. Take this B to be very small compared to A and X. Your mission is to determine the mutual inductance. So now how to solve this? Now these type of question looks super difficult, but they are, believe me, super easy. All you need to remember is that if you have a current carrying loop carrying a current I having a radius R, then the magnetic field due to this current carrying loop at a point at distance X on the axis is given by B equals to mu naught I into R square upon 2 times of R square plus X square raised to the power of 3 by 2. And if you know this, game over. So you will say, let's assume some current I1 flows in the first coil. My mission is to find the flux linked with the smaller coil due to the current in the bigger coil. That's my mission. So I will say that the flux linked with the smaller coil equals to the number of turns in the smaller coil multiplied by the magnetic field strength due to the bigger coil at position of smaller coil multiplied by the area of the smaller coil. This is the flux linked with the smaller coil. Now bachcho, here when you write the magnetic field, you will say that the magnetic field due to this bigger coil at position of smaller coil will be given by the number of turns in the bigger coil times mu naught I times the radius of the coil whole square A square upon 2 times of A square plus X square distance square raised to the power of 3 by 2. Once you know this, game over. You will say phi 2 equals to something times I1, and that something is the mutual inductance. So apart from I1, take everything together. Whole of this is your mutual inductance. So you will say mutual inductance comes out to be mu naught N1 and 2 pi A square B square upon 2 times A square plus X square raised to the power of 3 by 2. Let's practice one more example. Let's say here you have got an infinitely long current carrying wire, and there is a small coil of radius R placed at a distance A from the wire. It has got N turn. Question is, what is the mutual inductance for this system? So assume that some current I flows here and write down the flux linked with this loop due to this current, and you can write phi 2 equals to something times I, and that something is the mutual inductance. So if a current I flows here, you will say that the flux linked with this smaller coil will be nothing but its number of turn multiplied by the strength of magnetic field here multiplied by its area. So you write N into mu naught I1 upon 2 pi A into its area, which is pi R square. So you will cancel out pi, and you will write phi 2 equals to something times I1. So this something has to be your mutual inductance. So mutual inductance comes out to be mu naught and R square by 2. So what are you trying to justify here? Simple thing. Assume the current in one of them. Find the flux linked with second one. Once you have got flux linked with second one, you can write it as mutual inductance times current in the first one. Now let's see one more example of a solenoid in a solenoid before we move on to talk ahead. So now let's say you have got a smaller solenoid inside a bigger solenoid. The bigger solenoid has got number of turns per unit length N1. It has got a length L1, it has got a cross-sectional area A1, and the smaller solenoid has number of turns per unit length N2, it has got a length L2, and it has got a cross-sectional area A2. Your mission is to determine the mutual inductance of the system. What to do? Assume some current I1 flowing in the bigger solenoid And due to the current in this bigger solenoid, you can find out what is the flux linked with the smaller solenoid. You will say that the flux linked with the smaller solenoid will be nothing but the number of turns in the smaller solenoid, which is the number of turns per unit length multiplied by length, times the strength of magnetic field, which is mu naught N1 I1. The number of turns per unit length in the bigger solenoid, which is producing the magnetic field, is N1, and the current flowing in it is I1, times the area of the smaller solenoid, which is A2. Game over. You can say apart from this I1, everything that I have here is the mutual inductance. So you will get the mu2 equals to mu naught N1 N2 L2 A2 I1. Apart from I1, everything is your mutual inductance. So now let's talk more about mutual inductance. If you have got two coils of, let's say, self-inductance L1 and L2, if you have got two coils of self-inductance L1 and L2, and they are placed close by in different orientation, so we say that the mutual inductance of this combination is directly proportional to under root of the multiplication of their self-inductance. So mutual inductance proportional to root L1 and L2. Irrespective of the orientation, the mutual inductance for this pair will come out to be directly proportional to root L1 L2. And every time a physicist get a proportionality, they add up a proportionality constant. So here we get a proportionality constant and we call it K. We have got a special name for K. K is called coupling factor. Now, the more the number of magnetic field lines coming out of one passes through the second, the more will be the coupling factor and the more will be the mutual inductance. If I ask you, I have got two coils and I place them this separation apart, their mutual inductance will be more, and when I place them this separation apart, their mutual inductance will be more. You will say that, sir, when they are closer now, on driving the current in one, the number of magnetic field lines passing through the second one will be higher. So the flux linked with the second one will be higher. So the mutual inductance will be higher. So if you have got same two coils, you place them closer, more flux will be linked for the same current. So you will get higher mutual inductance. So understand that the mutual inductance for the pair is directly proportional to root L1 L2. And here we place a constant which is called coupling factor. Now remember that the greater the flux linked between the two coils, the greater is the coupling factor. And the maximum possible value of this coupling factor can be 1. So think of one case when you have got two coils of same length, same cross-sectional area, everything same, wrapped one over the other. So whatever magnetic field lines are produced by one, all of them will pass through the second one. So for such a case, when 100% of the magnetic field line produced by the one crosses the other, you say that the coupling factor is maximum equal to 1. And when the flux linked with the second coil due to the current in the first coil is 0, then you say that coupling factor is 0. Think of these two small coils placed with their planes perpendicular. The first coil produces some field, but there is no flux linked with the second coil because the area has not got magnetic field lines crossing them. The magnetic field lines lie in the plane of the area. So for such a case, you will say that the coupling factor is 0, and for such a case, perpendicular orientation, you will say that the mutual inductance is 0. Do understand that the maximum mutual inductance can be root L1 L2 when the coupling factor equals to 1. So now we will talk about the last topic, which is transformers. But a transformer is a very simple device. Understand that in a transformer, we take a soft iron core and we place winding on both of its sides. The side from where we give the input is called primary, and from the side we take the output is called secondary. Now you will say that, sir, why are you using a transformer? We use a transformer to increase or decrease the potential of an AC supply. Second question that should come in your mind is why we have used a soft iron core. We know that soft iron core is called soft iron core because it can be magnetized or demagnetized easily. So there is very small hysteresis loss. Now when some current flows in the primary coil, it produces magnetic field. And due to the magnetic field produced in the primary coil, and we have got iron core, which is ferromagnetic material, the same strength of magnetic field is found even inside the secondary coil. So if we have a transformer where we have got primary coil, secondary coil, and we have got this soft iron core connecting the primary coil and the secondary coil. If there is some magnetic field produced at the position of primary coil due to some current flowing in the primary coil, the same strength of magnetic field will be produced at the place of secondary coil. Now you will say that if the flux linked with one loop is phi, sir, for which one? Primary coil or secondary coil? It is going to be same. Why? Because the strength of magnetic field is going to be same. So what does this soft iron core do? It links the flux. Whatever will be the flux in the one turn of the primary coil, the same flux will be linked with one turn of the secondary coil. So what is the job of soft iron core? To link the flux. Now bachcho, think that if the primary coil has got number of turn Np and the secondary coil has got number of turn Ns, so you will say that the overall flux linked with the primary coil will be equals to the number of turns in the primary coil multiplied by the flux linked with one turn, which is fine. So you will say that the flux linked with overall primary coil equals to number of turns in the primary coil multiplied by the flux linked with one turn. The same thing can be said for secondary coil as well. You will say that the overall flux linked with the secondary coil equals to number of turn in the secondary coil multiplied by the flux linked with one turn. Now we know that the EMF induced in the primary coil equals to minus d phi p by dt, the rate of change of magnetic flux in the primary coil with respect to time, and the EMF induced in the secondary coil will be minus times the rate of change of magnetic flux in the secondary coil with respect to time. In place of the flux linked with the primary coil, substitute the number of turn in the primary coil multiplied by the flux with one turn, and in place of flux linked with the secondary coil to be the number of turn in the secondary coil multiplied by the flux linked with one turn. So here you will get EP equals to minus NP times d phi by dt. If you write EP equals to minus d of NP phi by dt, since the number of turn in the primary coil is constant, you can take it outside. And same can be done for secondary coil. You can say that the EMF induced in the secondary coil equals to minus times the number of turn in the secondary coil into the rate of change of magnetic flux with one of the turn. Now dividing both the sides, you will get EP by ES. And on the right hand side, minus d phi by dt minus d phi by dt get cancelled, you get NP by NS. So the EMF induced in the primary coil upon the EMF induced in the secondary coil equals to number of turn in the primary coil upon number of turn in the secondary coil. So think of it this way. If the number of turn in primary coil is 200 times the number of turn in secondary coil, if the number of turn in primary coil is 200 times the number of turn in the secondary coil, then the EMF induced in the primary coil will be 200 times the EMF induced in the secondary coil. So if the EMF induced in the primary coil comes out to be higher, it means that the input has got higher potential and the output has got lower potential. If the number of turn in the secondary coil, let's say, is 10 times the number of turns in primary, then this quantity, the number of turn in primary upon number of turn in secondary, will be 1 by 10. It means that the EMF induced in the secondary will be 10 times that of primary. So if in primary the input voltage is 220, so if the secondary has got 10 times the number of turn, the EMF in the secondary will be 10 times. So you will get 2200 volts. This is something easy and you should remember. So the side which has got more number of turns will have more EMF. Isn't this obvious? The flux linked with one loop is same. The side which has got more number of turns will have more flux linked to it. And when the current changes, the flux changes, it will have got more EMF linked to it. Now bachcho, there are two types of transformers. There is something called step-up transformer and there is something called step-down transformer. The job of step-up transformer is to increase the potential. So the input is low potential and the output is high potential. If you want the output to be higher potential, the EMF in the secondary to be greater than the EMF in primary, then better the number of turns in secondary should be greater than the number of turns in primary. To make the EMF 10 times, the secondary should have 10 times the number of turns. To make the output EMF 100 times, the secondary should have 100 times the number of turns. That's the basic idea. So for a step-up transformer, the output EMF is more than the input EMF. So the EMF in the secondary coil is more than the EMF in primary coil. And to make this happen, the number of turns in the secondary coil are kept more than the number of turns in the primary coil. Similarly, we have another type of transformer that is called step-down transformer. step down, the one which decreases the potential. So the input potential is high and the output potential is low. If the output potential is less, it means that the EMF induced in the secondary is less than the EMF in primary. If the EMF in secondary is less than the EMF in primary, it can happen only when the number of turn in the secondary are less than the number of turn in primary. So as to make the output potential 10 times smaller, the secondary coil should have 10 times smaller number of turns. So if the input coil, the primary coil has 200 turns and the secondary coil has got, let's say, 20 turns, it means that the secondary coil has got 1/10 the number of turns. So the flux linked with the secondary coil will be 1/10. So the rate of change of flux will be 1/10. So the EMF produced in the secondary coil will be 1/10. That is the basic idea. Now, bachcho, do understand step up transformers are used nearby the power plant. So once the power is created at the power plant, before supplying it into the grid, it is stepped up, the potential is increased. That's why by nearby many a power line you might have read 10,000 volt. Be careful, 10,000 volt. And when this power line comes within our colony, nearby our house, then there are step down transformers, because within our house the supply potential is 220 volt. So after creation of energy at the power plant, the potential is stepped up, then it gets supplied at the high potential. That leads to smaller power loss during the transfer of energy, and once it reaches our colony, it is then stepped down before supplying it into our house. So nearby our house we have got step down transformer, nearby our house we have got step down transformer, nearby power plant we have got step up transformer. This is something you should know. Now beta, one last thing here. If there is no power loss, then understand that the input power has to be equals to output power. And while teaching you power, I said that for entire course of electrodynamics, every time I say power, do not think of I square R, do not think of V square upon R, because that doesn't work everywhere. I square R and V square upon R work only for resistor. Whenever you have to think of power, now better think of IV. Now, if there is no power loss, then power input has to be same as power output. So I can say that the EMF in the primary times the current in the primary equals to EMF in secondary times the current in the secondary. From here, one can even write that EMF in primary upon EMF in secondary equals to current in secondary upon current in primary. So if, let's say, in the primary coil you have got 200 turns and in secondary coil you have got, let's say, 50 turns. So first of all, tell me, this is a step up or step down? Since the number of turns in the secondary are 1/4, the flux linked with the secondary is always 1/4. So the rate of change of flux in the secondary will be 1/4. So if the input potential is V, output potential will be V by 4, right? Second, bachcho, if there is no power loss, then if the input current is I, the output current has to be 4I, so that the input power is same as the output power. So these are the small things that you should know about transformers. That's all in this hour. See you guys in next hour, where we will start the topic of AC. So that's all for now. See you guys in the next hour.